Section 20.1 Crystal Field Theory F. Square planar complexes. When a transition metal center is bonded to 4 identical ligands, usually its structure is a tetrahedral structure predicted by VSEPR theory, valence shell electron pair repulsion, because we like to separate these 4 ligands as much as possible to reduce the repulsion between these ligands as much as possible. But sometimes we do observe square planar structures for some transition metal complexes. And whenever you see a square planar transition metal complex, 90%, 95%, the transition metal center has a 4D8 or 5D8 electron configuration, such as platinum 2+, gold 3+, iridium plus, palladium 2+. So they all have 4D8 or 5D8 electron configuration. Why is that? Well, we'll have to review the electronic structure of the octahedral transition metal complex first. So now let's look at this comprehensive illustration. I got it from libretext.org. This is just a transition metal cation with 5 degenerate d orbitals. And now we put a spherical shell of negative charges surrounding this transition metal. That will bump up the energy of these 5 d orbitals. But because this negative charges has also a spherical symmetry, these 5 d orbitals are still degenerate. And then we will change the environment from the spherical symmetry to octahedral symmetry. So now right here we have only 6 negative charges. Those are point charges. And these 6 negative charges will affect the energies of these d orbitals in 2 different ways. The reason is this. If you look at the dz squared orbital, it's going to be pointing toward this negative charge on top and also this one on the bottom. There is stronger repulsion between dz squared and these 2 negative charges. Similar here, dx squared minus y squared has 4 lobes pointing towards these 4 negative charges in the middle. And that makes these 2 orbitals have higher energy than these 3 orbitals. These 3 d orbitals are not pointing directly to any of these negative charges. And we call this energy splitting. This delta O means the energy difference between these 2 doubly degenerate each orbitals and these 3 triply degenerate d orbitals. O stands for octahedral. And over here, this energy level is called the barycenter, and these 2 orbitals are 0.6 delta O above the barycenter. These 3 triply degenerate orbitals are 0.4 delta O below the barycenter. So over here, this energy decrease is due to the electrostatic attraction being taken into account. So of course, there's going to be attraction between this nucleus and all these negative charges. So, but don't worry about this energy increase, this energy decrease. Just focus on the middle 2 pictures to understand the splitting of the d orbitals. And now I'm going to show you the shapes of these d orbitals and I will show you why this dz squared orbital and dx squared minus y squared orbital have higher energy than the other three. So again, if you look at this orbital, these two yellow lobes are pointing directly towards these two negative charges. These are very close to each other, and these are very close to each other. That bumps up the energy of dz squared. That means if you put electrons in this orbital, this electron will feel a greater repulsion than if you put the electron in here. Similarly, if you look at dx squared minus y squared, you'll see these four lobes are pointing toward these four negative charges. And that increases the energy of this orbital as well. It turns out these two orbitals both go up by the same amount. So these two will be doubly degenerate EG orbitals. These three d orbitals with four lobes are not pointing directly towards those negative charges. Therefore, they have lower energy than these two. These three are triply degenerate T2G orbitals. So again, I got this picture from librarytext.org. So you can click this link to look at their pictures and descriptions. Now we're going to remove two negative point charges. I will remove this one and this one. How does that affect the energy of this dz squared orbital? Well, very simple. Removing these two negative charges will significantly reduce the repulsion this orbital feels. That means removing these two negative charges will dramatically reduce this dz squared orbital energy. Alright? And also here, because these two lobes are not, although they are not directly pointing up, but they are above the z equals 0 plan, so these two are closer to this negative charge than this 4. These two lobes are closer to this negative charge than this 4. Similarly, over here, if you look at dyz, we have a similar analysis that tells us removing this negative charge and this negative charge will also reduce the electron repulsion between this orbital or this orbital and the surrounding ligands. In summary, by removing this negative charge and this negative charge, we will significantly decrease the dz squared orbital energy. We will also decrease the energies of the dxz and dyz orbitals. Well, what about this dxy and dx squared minus y squared orbitals? Well, of course, if you remove two negative charges, they will also feel less repulsion. But I want to remind you, they are really far away from these two negative charges in the first place. So removing these two negative charges has very little effect on the orbital energies of dxy and dx squared minus y squared. Alright, now let's look at the energy diagram of the square planar structures. So this is octahedral complex. We have this two on top, this three on the bottom. On top you have dz squared, dx squared minus y squared, doubly degenerate EG orbitals. On the bottom, dxy, dyz, dxz are triply degenerate T2G orbitals. These two orbitals are 0.6 delta O above the barycenter. These three are 0.4 delta O below the barycenter. And the barycenter is just the average. Now let's remove the two negative charges along the z direction. That will dramatically reduce the energy of this dz squared orbital all the way down here. And then it's going to also decrease the energies of the dyz and dxz orbitals. So down here. Alright? So this energy decrease is just qualitatively described here. Okay, dz squared can be here, or even above this one. So it really depends. It really depends. Whether it's a 3D orbital, or 4D z squared orbital, or 5D z squared orbital. So there's significant difference. Alright? But now if you look at just this new energy diagram, you will see. Now you have 1, 2, 3, 4. There's 4 orbitals, all below the previous barycenter. Only one orbital, dx squared minus y squared, is still above the barycenter. So over here, this is barycenter over here. So in this case, we can imagine that 1, 2, 3, 4. This 4 d orbitals can accommodate 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And that's why when you see a square planar structure of a transition metal complex, this transition metal is very likely 4d8 or 5d8 electron configuration. Why not 3d8? Well, when you have 3d8, the overlap between the 3d orbitals and the ligands is not as significant as the interaction between 4d8 or 5d8 and the ligands. So the energy decrease is not as significant. So perhaps you can still lower this dz squared to maybe here, but it's still above the barycenter, right? And you can slightly lower the energies of dyz or dxz, actually both of them, maybe to here and here, but the energy decrease is not significant enough. Alright? So for 3d8 transition metal center, when they are bonded to 4 ligands, still they prefer to adopt a tetrahedral structure. Only when you have 4d8 and 5d8 transition metal centers, for example, palladium and platinum 2+, gold 3+, iridium 1+, and then we have this kind of energy diagrams, and then we can tell there's 4 d orbitals welcome 8 electrons, because the energies of these 8 electrons will all be lower than the barycenter. So again, let's compare square planar complexes and tetrahedral complexes. When you have 4d8 or 5d8 metal ions, it's more likely to form a square planar complex with 4 ligands. And this is because of the large energy decrease from here to here after removing the 2 negative charges along the z-axis. Okay? And also the electron pairing energy in 4d and 5d orbitals is small, because 4d and 5d orbitals are more diffuse. It's easier for the electrons in the 4d or 5d orbitals to avoid each other, so there's lower electron pairing energy, and that will further favor the low spin square planar structure. Okay, again, 8d electrons occupying this 4 orbitals will have all electrons paired. Now let's get back to 3d8 metal ions. For example, nickel 2 plus has 8 d electrons. It prefers to form a tetrahedral structure. For example, this tetrachloride nickelate. This is because the additional ligand field stabilization energy in the square planar structure is insufficient to compensate the larger repulsion between the 4 ligands in a square planar structure. Because after all, the bond angle is only 90 degrees in the square planar structure. It's 109.5 degrees in the tetrahedral structure. So in this case, the VSEPR theory wins. But still, there are exceptions. 3d8 metal complexes can adopt the square planar structure if it's bonded to strong field ligands such as carbonyl ligands, cyanidal ligands, and triphenyl phosphenyl ligands. So in this case, they prefer to adopt the square planar structure because this ligand field stabilization energy, LFSE, is big enough to compensate the larger repulsion between the 4 ligands in the same plane. So this is one example. When this nickel 2 plus is bonded to 4 cyanidal ligands, the structure is going to be square planar.